Hello everyone, I'm Professor Chia-Po Wei. From week 10, this course is taught by me. If you need any assistance, you can write emails to me. When writing emails, please inform me of your name, student ID, and class. There will be an examination held on April 28. This examination is handled by Professor Gao Chongyao and his teaching assistants. Please see the announcement board of the Cyber University. And I will post the course information both on the announcement board of Cyber University and the following course website. And I still use remote teaching because due to the COVID-19 outbreak, the school suggests us to use remote teaching to prevent group infection. So I will use pre-recorded online courses, which are available both in English and in Chinese. And we will still have a weekly quiz. And the time is Monday 8:30 a.m. And we also use the Cyber University to test. The teaching assistants are changed. The teaching assistants will be my students. The TA hours are Tuesday 16 to 18 and Thursday 10 a.m. to 12 a.m. at the EC building of A011-2. If you go to the course website, on the top there will be a news section. I will post the information of examination, weekly quiz, or grades in this section. Below is the course information. You can find my email as well as the teaching assistant's name, including their email. And the TA hours are also listed here. In the bottom of this page is the schedule of this course. I will upload the slides and the videos of each week and post the link here. This is the title page of the slides. On the top right corner, this is the date when the slides are created. In the following pages on the top right, there will be a page number. This is the page number of the textbook. If you need any detailed information of this page, you can refer to the textbook. Next, I will revisit what we have learned about linear algebra. In Chapter 1, we have learned how to solve linear equations. In Chapter 2, we learned how to calculate determinants. Now we are in Chapter 3, vector spaces. Here, vector is an abstract math object. Each vector has two kinds of operations. The first operation is vector addition. Then the second operation is scalar multiplication. Based on these two operations, we can define the concept of linear combination or span. And the next, we can define the notion of linear independence. Then we can, based on linear combination and linear independence, we can further define the notion of basis. In section 3.5, we are going to introduce the change of basis. This section is very critical because it defines the notion of coordinates, and this notion is closely related to section 4.2 matrix representations and 4.3 similarity. If you do not have the idea of coordinates defined in section 3.5, then you will not be able to understand the contents of sections 4.2 and 4.3. Next, I will revisit the notion of basis and use this as an example for illustrating how to learn linear algebra. In Chapter 3, we encounter many abstract ideas. We encounter many abstract concepts. How do we learn these abstract concepts? The first thing we can do is not to memorize the definition of these concepts. Because if we force ourselves to memorize these definitions without comprehension, this knowledge will only enter our short-term memory. A few months later, this knowledge will disappear from our memory. So, force ourselves to memorize definitions can only help us to pass the exam, but in the long run, it is not very useful. On the other hand, a better way to learn these abstract concepts is to try to understand, to comprehend why this definition has those properties. Because if we try to understand or comprehend something, those knowledge will enter our long-term memory, and this will help us to quickly familiarize many closely related concepts. So in the long run, it pays off. So it is a better way to understand rather than to memorize the definition. We say a set of vectors v1, v2 to vn is a basis for a vector space V if these vectors satisfy the following two properties. The first property is that these vectors need to be linearly independent. The second property is that these vectors need to span V. Here, span means if we randomly pick one vector from V, then this vector can be represented as a linear combination of v1, v2, and vn. It is intuitive to have property 2 because we want a set of vectors that can represent the vector space. Then we turn to the property 1. Is it necessary to have v1 to vn to be linearly independent? We can ask another question. What happens if v1, v2, vn are linearly dependent? For linearly dependent, this means among the n vectors, there will be some vector that can be represented as a linear combination of other vectors. In other words, there will be redundant vectors among these n vectors. And redundancy is not the thing we want. Well, we always want a set of vectors to be as compact as possible. So this is the reason why a basis to have the following two properties. Next, I will define the notion of dimension for a vector space V. Let's consider the vector space R3. What do we mean dimension for the vector space R3. It is intuitive to consider R3 to have dimension 3, since it has 3 freedom, x, y, z. But what is the precise definition? Below is the standard basis for R3, and any vector in R3 can be written as C1 times the first vector plus C2 times the second vector plus C3 times the third vector. And the number of freedom is the number of coefficients C1, C2, and C3. So the dimension is actually the number of vectors in a basis. So we will use the number of vectors in the basis to define the dimension of a vector space. I will give some basis examples. The first example is the Euclidean vector space R3. In R3, the standard basis is 1, 0, 0, 0, 1, 0, and 0, 0, 1, which is denoted by E1, E2, and E3. This is the standard basis for R3. Below, this page shows another basis for R3. This basis is 1, 1, 1, 1, 1, 0, and 1, 0, 0, which is denoted by V1, V2, and V3. To prove V1, V3, V2, and V3 is a basis for R3, we need to show that V1, V2, and V3 can span R3. So we pick random one element from R3, which has the form alpha, beta, gamma, and express this vector as a linear combination of the three vectors v1, v2, and v3. And its coefficients, the linear combination coefficients, are C1, C2, and C3. Given alpha, beta, gamma, and the three vectors v1, v2, v3, our goal is to solve the coefficients of the linear combination C1, C2, and C3. For this example, after some computation, we obtain C1 equals gamma, and C2 equals beta minus gamma, and C3 equals alpha minus beta. So given any vector in R3, we can always express the vector in terms of the linear combination of v1, v2, and v3. So we have proved v1, v2, and v3 can span R3. Next, we show v1, v2, v3 are linearly independent. Based on the definition of linear independence, we need to prove that d1, v1, we need to solve the equation d1, v1 plus d2, v2 plus d3, v3 equals the zero vector in R3. After solving this equation, we obtain d1 and d2 and d3 all equals 0. So this equation only has the zero solution, and therefore v1, v2, v3 are linearly independent. Until now, we have proved v1, v2, v3 span R3, and they are linearly independent. So v1, v2, v3 is a basis of R3. The second basis example is P3. polynomials of degree less than 3. The vector in P3 has the form alpha plus beta x plus gamma x squared. The standard basis for P3 is 1x and x squared. Below we show another basis for P3. Consider the three vectors 1 minus x squared and x plus 2 and x squared. We want to show the three vectors forms a basis for P3. The first thing we want to prove is that the three vectors can span P3. So we random pick one vector in P3, alpha plus beta x plus gamma x squared, and express this vector as a linear combination of the three vectors. Now we need to solve C1, C2, and C3 that satisfies this equation. To solve this equation, we need to compare the coefficient of the constant. On the left-hand side, the coefficient of the constant is alpha, while on the right-hand side, the coefficient of the constant is C1 times 1 plus 2 times C2. And we compare the coefficient of x. On the left-hand side, the coefficient of x is beta, while on the right-hand side, the coefficient of x is C2. So C2 must equals beta. If we compare the coefficient of x squared, then we have gamma equals minus C1 plus C3. In the end, we will have C1 equals alpha minus 2 beta, and the C2 equals beta, and the C3 equals alpha minus 2 beta plus gamma. Therefore, given any vector in P3, we can always express it as a linear combination of the three vectors. So the three vectors is indeed can span P3. Next, we show that the three vectors are linearly independent. Based on that definition, we need to consider this equation. This equation is the linear combination of the three vectors that equals the zero vector in P3. The zero vector in P3 has the form 0 plus 0x plus 0x squared. Again, we need to compare the coefficients, and then we can solve D1, D2, and D3. After some computation, you can obtain D1 equals D2 equals D3, and they must be all 0. Hence, this equation only has the zero solution, and the three vectors are therefore linearly independent. So we have proved the three vector can span P3, and also they are linearly independent, and hence this three vector is indeed a basis for P3. The third basis example is 2 times 2 symmetric matrices. And this example does not appear in the textbook, and this example is actually created by myself. And the vector in this vector space has the form. It is symmetric, means this 2 times 2 matrix equals its transpose. So it has this form. The standard basis for this vector space is E1, E2, and E3. And the E1 is the 2 times 2 matrix, 1 0 0 0, and E2 is the 2 times 2 matrix 0 1 1 0, and E3 is the 2 times 2 matrix 0 0 0 1. Below we will show another basis for this vector space. Consider the three vectors v1, which is 1 0 0 1, and v2 v2 is the 2 times 2 matrix 1 1 1 0, and v3 is the 2 times 2 matrix 0 1 1 1. And the first thing is that we want to show v1 v2 v3 can span this vector space. So given any vector in S2 times 2, it has the form alpha, beta, beta, gamma. And the linear coefficients are C1, C2, and C3. By solving this equation, we can obtain the coefficients are by solving these equations, we can obtain these linear coefficients. This means given any vector in this vector space, we can always express it as a linear combination of v1, v2, and v3. So v1, v2, v3 spans this vector space. Next, we want to prove v1, v2, and v3 are linearly independent. This means we have to solve the equation in the bottom of this page. We need to consider the linear combination of v1, v2, and v3 equals the zero vector in S2 times 2. The zero vector in S2 times 2 is a 2 times 2 zero matrix. By solving these equations, we can obtain C1, C2, C3 must be all zero, and therefore we have proved v1 and v2 and v3 are linearly independent. So because the three vector satisfies the two properties of basis, so we have proved v1, v2, and v3 is indeed a basis for S2 times 2. We have seen three basis examples. The first example is R3, the Euclidean vector space. The second example is P3, polynomials of degree less than 3. The third example is S2 times 2, the vector space of 2 times 2 symmetric matrices. The three vector spaces look very different, but they share some common properties, such as vector addition and scalar multiplication. They also share the same notions, such as linear independence and linear combination. By defining these abstract notions, mathematicians have created a uniform way to process these vector spaces. There is no need to separately handle each special case. We can focus on developing results based on abstract notions. Once the result is proved, it can be applied to all the vector spaces. This is the advantage of abstract notions. This is also the reason why the mathematician favor the use of abstract notions. Once we have a basis, we can use it to define coordinates. What do we mean by coordinates? Consider a point 2, 1 in the R2 Euclidean vector space. Here 2 means 2 units along the x-axis, while 1 means 1 unit along the y-axis. In this page, I will give the precise definition of coordinates. Uh, X can be written as the sum of U and V, where U is 1, 0 and V is 0, 1. And we often use E1 to denote 1, 0 and E2 to denote 0, 1. E1 and E2 is called the standard basis for R2. And the coordinates are the coefficient of the linear combination. So 2, 1 is actually the coefficients. We will use the notation x bracket and the subscript e to denote the coordinate vector of x with respect to basis e. For this example, e1, e2 is the basis e, and the coordinate vector of x with respect to e is 2, 1. Note that the coordinate vector is in R2. This page shows another coordinate example. Consider the vector space of R2, and the YZ is a basis of R2, and we use E to denote this basis. And suppose S is the sum of 3Y and 2Z. Then the coordinate vector of X with respect to E is 3, 2. 3, 2 is the coefficient of the linear combination 3y plus 2z. Note that the order is important. If we change the order from yz to zy, then the coordinate also changes. It changes from 3, 2 to 2, 3. Below, I will give the precise definition of coordinates. For suppose v1, v2, and vn is a basis for the vector space V, and we use E to denote this basis. And suppose the vector x with respect the coordinate vector of x with respect to E is C1, C2 to Cn, which is in Rn. This notation means that x can be written as the linear combination of the basis, while the coefficients of the linear combination is the coordinates C1, C2 to Cn. Notice that here the vector space can be polynomial, can be matrix, can be continuous function, but the coordinate vector is always in Rn. Here, n is the number of vectors in the basis, and n is also the dimension of the vector space. I will give 3 coordinate examples in this page. The first example is in R3. Suppose E is a basis of R3. Note that each vector in E is in R3. And suppose the coordinate of x with respect to E is 5, 6, 7. Then this means x is the linear combination of the basis, while the coefficients are 5, 6, 7. The second example is the polynomial vector space P3, and we also have a basis E, and each vector in the basis is a polynomial. Suppose the coordinate of x with respect to E is 5, 6, 7. Then this means x can be written as the linear combination of the 3 polynomials with coefficients 5, 6, 7. And it is in this example x is in P3. The third example is the 2 times 2 symmetric matrices, S2 times 2. Suppose E is a basis for S2 times 2. Then each vector in E is a 2 times 2 symmetric matrix. Suppose the coordinate vector of x with respect to E is 5, 6, 7. Then this means S can be written as the linear combination of the bases with the coefficients are 5, 6, 7. And the x is in the vector space S2 times 2. We know that for these three examples, the vector space are different. The first vector space is R3. The second vector space is the polynomial P3. The third vector space is the symmetric matrix S2 times 2. But their coordinate with respect to a basis is always R3. By using the notation of coordinates, we have a uniform way to process all these three different vector spaces. The next example is exercise 4, which is from page 172 of the textbook. In this example, we will learn how to compute the coordinate vector with a given basis in R2. Let x be a given vector in R2, and our goal is to compute the coordinate of x with respect to a given basis in R2. Suppose the coordinate of x with respect to E is C1, C2, then this means C1 and C2 satisfy this equation. That is to say, x is the linear combination of the bases, where C1 and C2 are the coefficients of the linear combination. Solving these two equations, we obtain C1 equals -1 and C2 is 2. Hence, we obtain the coordinate vector of x with respect to the given basis E. In this page, I will give the motivation for learning the change of basis. Suppose our goal is to compute xn, which equals an, matrix A of power n, which means multiply itself n times. An times x0, and A is a given matrix of dimension d times d, and x0 is a given vector in Rd. Note that it is computationally expensive to compute an if n or d is large. If n is large, this means we have to multiply a many times. If d is large, means the dimension of a is large, so each multiplication will be very expensive. For ease of illustration, let D equals 2. In this case, A is a 2 times 2 matrix. Now suppose we can find scalars lambda 1, lambda 2, and vectors u1, u2 such that AU1 equals lambda 1 u1 and AU2 equals lambda 2 u2. Actually, you have already know how to do this. Lambda 1, lambda 2 are eigenvalues of A, and u1 and u2 are the corresponding eigenvectors of A. If we can express x0 as the linear combination of u1 and u2, then we can substitute this expression into x0 and obtain C1 an u1 plus C2 an u2. Now know that u1 is an eigenvector of A, so an u1 becomes lambda 1 and u1. And similarly, u2 is an eigenvector of A, so an u2 can be written as lambda 2n u2. It is much faster to compute the power of a scalar than to compute the power of a matrix an. So we have greatly reduced the computational costs. In this example, we can view the x0 as the coordinate vector to the standard basis in RD. If we can transform x0 into another coordinate system defined by the eigenvector of matrix A, then in this new coordinate system, the multiplication of an of x0 would become very easy. In this page, we will learn how to change coordinates between bases in R2. Let u1, u2 be a basis in R2, which is denoted by F. Suppose X is C1 U1 plus C2 U2. Our goal is to find its coordinates with respect to the standard basis E1, E2, which is denoted by E. To this end, we want to express X as the linear combination of E1 and E2 with coefficients x1 and x2. Know that we can rewrite C1 U1 plus C2 U2 as a matrix S times C1 C2. Here S is the matrix formed by staking U1 and U2 horizontally, so S is a 2 times 2 matrix. Similarly, we can rewrite S1 E1 plus S2 E2 as the matrix E1 E2 times S1 S2. Here, the matrix I is formed of staking E1 and E2 horizontally, so matrix I is a 2 times 2 identity matrix. Then we arrive at the equation matrix S times coordinate of X with respect to F equals coordinates with respect to E. And we call the matrix S is the transition matrix from U1, U2 to E1, E2. We also have this equation. This equation is obtained by multiplying both sides of S inverse. The matrix inverse exists because because the matrix S is non-singular. It is easy to verify that because U1 and U2 are linearly independent since it forms a basis in R2. So U1 and U2 are linearly independent, which can imply matrix S is non-singular. Then from this equation, we see that we call that matrix S inverse is the transition matrix from E1, E2 to U1, U2. From this equation, we see that matrix S send every coordinate with respect to F to coordinates with respect to E. So S is the transition matrix from U1, U2 to E1, E2. And from this equation, we see that S inverse converts coordinates with respect to E to coordinates with respect to F. So we code S inverse the transition matrix from E1, E2 to U1, U2. In this page, I will illustrate example 2 in page 167 of the textbook. Let U1 and U2 be a basis in R2. And given X be 7, 4 in R2. Our goal is to compute the coordinate of X with respect to F. Here I will present two methods. Method 1 is based on the definition of coordinates. So to compute the coordinate of X with respect to F, we have to write S as the linear combination of U1 and U2. This means after substitute U1 and U2 into this equation, we have this. And here C1, C2 are the coefficients of the linear combination. And there are two equations. After solving the two equations, we can obtain C1 is 3 and C2 is -2. And this is the coordinates with respect to basis F. Method 2 use transition matrix to compute the coordinate with respect to basis F. Know that C1 U1 plus C2 U2 can be written as the matrix U times C1 C2. Here, matrix U is formed by stacking U1 and U2 horizontally. So U1, U2 is a 2 times 2 matrix. And matrix U are already known since U1 and U2 are given. Now our goal is to compute C1, C2, so we multiply the inverse of U on both sides and obtain this equation. Now we multiply U inverse with X. X is 7, 4. Then we can obtain the value of C1 and C2. So the value of C1 and C2 is 3 minus 2, which is consistent with the answer obtained by method 1. We know that method 2 is only applicable when the vector space is Rn. When vector space is not Rn, for example, if the vector space is the polynomial, then we cannot use method 2. Because we can, if U1 and U2 are polynomial, we cannot directly staking the two vectors as a matrix. That is, when U1 and U2 are polynomials, staking the two vectors as a matrix is not legal. I have presented two methods for calculating the coordinate of X with respect to F. You can decide to use which method. Personally, I prefer method 1 because it is more because if you use method 2, you need to calculate the inverse of matrix U, which is more difficult. But if you use method 1, then you just follow the definition of coordinates, and there is no need to compute the inverse of a matrix. So I prefer method 1 for computing the coordinate of X. And the textbook only presents method 2. In this page, I will illustrate how to change coordinates between different bases in R2. Let U1, U2, and V1, V2 be two bases in R2. Our goal is to compute the transition matrix from V1, V2 to U1, U2. Once we obtain the transition matrix, we can convert the coordinates from V1, V2 to the new coordinate systems U1, U2. Given any vector x in R2, x can be expressed as the linear combination of V1 and V2, since V1 and V2 span R2. Similarly, we can express x as the linear combination of U1 and U2, since U1 and U2 is a basis of R2. Then we can rewrite D1V1 plus D2V2 as the matrix V times D1D2. Here we stake the two vectors V1, V2 horizontally as the matrix V, and V is a 2 times 2 matrix. Similarly, we can rewrite C1U1 plus C2U2 as the matrix U times C1, C2. Here, the matrix U is a 2 times 2 matrix. Note that the matrix U is non-singular, since the columns U1 and U2 are non-singular. So we can multiply U inverse on both sides and obtain this equation. This equation is U inverse V times D1, D2 equals C1, C2. So the transition matrix from V1, V2 to U1, U2 is U inverse V, because the matrix U inverse V sends coordinate with respect to V1, V2 to coordinates with respect to U1, U2. Note that this way to compute the transition matrix is only valid when the vector space is Rn. If the vector space is not Rn, we cannot use this method to compute the transition matrix, because for example, if the vector space is the polynomial, then if we stack the polynomial as the columns of a matrix, this is not legal, since the entries of a matrix must be a real scalar, not the polynomial. So this method is only valid when the vector space is Rn. In this page, I will illustrate exercise 7 in page 172 of the textbook. And given a basis V1, V2, and a transition matrix S, our goal is to compute W1 and W2 such that S is the transition matrix from W1, W2 to V1, V2. The goal is different to what we have learned. In the previous slide, we are given two bases in R2, and our goal is to compute the transition matrix from one basis to another. Now, in this slide, our goal is changed. We are given only one basis and one transition matrix. Our goal is to compute the other basis W1, W2, such that S is the transition matrix from W1, W2 to V1, V2. Denote W1, W2 as F, and denote V1, V2 as E. Recall that the transition matrix satisfies that matrix S times the coordinate of x with respect to f equals the coordinate of x with respect to e for any x in R2. The key to solve this exercise lies in how we can use this formula of transition matrix. If we pick x as W1, then the above equation would become W1E equals S times W1F. Now we substitute S into this equation and know that the coordinate of W1 with respect to F is 1, 0. Because W1 is the first element in the basis F. So W1, the coordinate of W1 with respect to F is 1, 0. After multiplication, we obtained 3, 1. And so the coordinate of W1 with respect to E is 3, 1. Then by definition, we have W1 can be written as the linear combination of V1 and V2, and the V1 and V1 V2 is the basis E, and the coefficients are the coordinate 3, 1. So after substitute V1 and V2, we will have W1. Similarly, if we pick x equals W2, then the transition matrix formula becomes this equation. This equation says that W2E equals S times W2F. And here, the coordinate of W2 with respect to basis F is 0, 1. Since W2 is the second element in basis F. So the coordinate of W2 with respect to basis F is 0, 1. Now after the multiplication, we obtained 5 minus 2. So the coordinate of W2 with respect to basis E is 5 minus 2. And by the definition of coordinate, we know W2 is the linear combination of V1 and V2, where the coefficients are 5 and minus 2. By substitute V1 and V2, then we obtained W2. In the previous slides, we have learned how to compute transition matrix for the spatial vector space Rn. In this page, we will learn how to compute the transition matrix for the general vector spaces. The general vector space can be polynomials, can be continuous functions, can be matrices. Denote W1, W2 to Wn as F, and denote V1, V2 to Vn as E. Then F and E are two bases for the vector space V. Our goal is to compute the transition matrix S from F to E, and recall that the transition matrix satisfies this equation for any vector x in the vector space V. This equation says that S times the coordinate with respect to F equals the coordinate with respect to E. This equation must hold for any x in the vector space. The key to compute the transition matrix lies in how we use this formula. If we pick x as W1, then the right hand side of this equation becomes S times W1F. Here W1F is 1 0 0 0 because 1 times W1 plus 0 times W2 plus 0 times Wn equals W1. Hence, hence E1 that is 1 0 0 0 is the coordinate of W1 with respect to F. Now if we partition the matrix S as S1, S2, and Sn, here Si is the ith column of the matrix S. Then if we multiply matrix S with E1, then we obtain S1. S1 is the first column of matrix S. So we have obtained S times W1F equals S1. S1 is the first column of S. Similarly, we can pick X as W2. Then the left hand side of the equation becomes S times W2F. Here W2 the coordinate of W2 with respect to F equals 0 1 0 0 0, which is E2. Because 0 times W1 plus 1 times W2 plus 0 times W3 plus 0 times Wn would equal W2. Hence, E2 is the coordinate of W2 with respect to basis F. Then if we multiply S with E2, and we will obtain S2, which is the second column of matrix S. Finally, we will have this equation for I from 1, 2 to n. Recall that the transition matrix satisfies S times x with respect to F equals x with respect to E for any x in the vector space. If we pick x as Wi, then the above equation will become S times Wif equals Wie. In the previous slide, we have proved that S times Wif would equal Si. Si is the ith column of matrix S. So we will have Si equals Wi with respect to basis E. If we can compute Wi with respect to E, then we will have the ith column of S. This is our goal. We want to compute the transition matrix. Suppose W1 can be written as the linear combination of B1, B2, and Bn with the coefficients S11, S21, and Sn1. Then the coordinate of W1 with respect to E would be S11, S21 to Sn1. And this is the first column of matrix S. Notice that in this equation, V1, V2 to Vn are given, and W1 is also a given vector. The only unknown are S11, S21 to Sn1. So this is a linear equation. Once we solve this linear equation, we can obtain S11, S21, and Sn1. That is, we obtain the first column of matrix S. Notice that this equation always have a unique solution, because W1, W2, Wn is a basis for the vector space V, and W1 is a vector in the vector space. So W1 can always be uniquely represented as the linear combination of V1, V2 to Vn. Following the similar procedure, we can express W2 as the linear combination of V1 to Vn and denote the coefficients s by s12, s12, s22 to sn2. Then then this s12, s22, and sn2 actually is the coordinate of W2E. W2E is the second column. W2E is the second column of matrix S. Following the similar procedure, we can compute each column of the matrix S, and finally we obtain the transition matrix. In this slide, I will illustrate example 6, which is in page 171 of the textbook. Given two bases E and F for the vector space P3. P3 is the vector space of polynomials of degree less than 3. Our goal is to compute the transition matrix from E to F. If S is the transition matrix from E to F, then it satisfies this equation for all x in the vector space P3. The key to compute the transition matrix lies in how we can properly select x. If we denote E as the source basis and denote F as the target basis, typically we will select x as the elements in the source basis E. Now we replace x with the first element in the source basis. Then the equation will become s times 1e equals 1f. Also recall that in the previous slide we have proved s times w1if equals the ith column of s. So now we have s times s times 1e equals the first column of the transition matrix, and we also have s1 equals 1f. 1f is the coordinate vector of 1 with respect to the basis f. Thus, if we can obtain the coordinate vector of 1 with respect to f, then we obtain the first column of matrix S. So to this end, we express 1 as the linear combinations of the basis f with coefficients s11, s21, and s31. By comparing the coefficients on the left hand side and the right hand side, we know that s11 plus minus 2 times s31 equals 1. And we also know s21 times 2 must equal 0, because on the left hand side there is no x term. We also know 4 times s31 must equal 0, because on the left hand side there is no terms of x squared. So finally we have s11 equals 1, and s21 equals 0, and s31 equals 0. And this is the first column of the transition matrix. Following the same procedure, if we pick x as the second element in the source basis, then we obtain that S2 equals SF. That is, the coordinate of x with respect to f is the second column of the transition matrix. So we express x as the linear combination of the basis f with coefficients s12, s22, and s32. Similarly, by comparing the coefficients on the left-hand side and the right-hand side, we can obtain S11, S22, and S32, which is the second column of the transition matrix. Next, if we select X as the third element in the source basis, then we obtain that the third column of the transition matrix would be the coordinate vector of x2 with respect to basis f. So we need to express x squared as the linear combination of basis f with coefficients s13 and s23 and s33. After some computation, we can obtain these three scalars, and s13, s23, and s33, which is the third column of matrix S. Next, I present the second method to solve example 6. Our goal is still the same, to compute the transition matrix from E to F. And to this end, first we compute the transition matrix T from F to E. Notice that the source target becomes F, while the target basis becomes E. Once we compute the transition matrix T, then its inverse, T inverse, is the transition matrix from E to F, which is our goal. To compute the transition matrix from F to E, we will use the formula of transition matrix, that is T times x with respect to F equals x with respect to E for all x in the vector space P3. To compute the transition matrix, we need to properly select x from P3. The key ideas are the same. The idea is to select x as the element in the source basis. Now the source basis is f, so we will select x as 1 and 2x and 4x squared minus 2. Now if we replace x with 1, then the formula of the transition matrix becomes T times 1 with respect to F equals 1 with respect to E. From the previous slides, we also know that T times 1 with respect to F equals T1, which is the first column of the transition matrix. If we can compute the coordinate of 1 with respect to E, then we can obtain the first column of matrix T. And so to this end, we express 1 as the linear combination with respect to basis E. Basis E is 1x and x squared. And this is the standard basis for P3, so it is quite easy to compute the coefficients of the linear combination. and the t1 is 1, 0, 0. Similarly, if we replace x with the second element in the source basis, if we replace x with 2x into the formula of transition matrix, then we obtain t times 2x with respect to f equals 2x with respect to e, and this coordinate would be the second column of the transition matrix T2. If we pick x as the third element in the source basis, that is, if we pick x as 4x squared minus 2, then the formula of the transition matrix becomes this. Here T3 is the third column of the transition matrix, which equals the coordinate of 4x squared minus 2 with respect to e. Once we obtain T1, T2, T3, then we have the transition matrix from F to E. Our goal is to compute the transition matrix from E to F, so T inverse is the final result. I have presented two methods for computing the transition matrix. Method 1 uses the definition of the transition matrix, while method 2 first compute the transition matrix from F to E. Here E is the standard basis, so the transition matrix would be very easy to compute. However, method 2 requires to compute T inverse in order to have the transition matrix from E to F. It will cost you a lot of time to compute T inverse. So personally, I would prefer method 1 to method 2. Since method 1 you only follow the formula of the transition matrix, and there is no need to compute the inverse of a matrix. Once we compute the transition matrix from E to F, then we can use the transition matrix to convert any coordinate from E to F. Below is an example. Consider the polynomial a plus bx plus cx squared. Then the coordinate of x with respect to E is abc. If we multiply the transition matrix with the coordinate vector with respect to E, then we obtain this vector. This vector is the coordinate with respect to basis f, which means x can be written as the linear combination of the basis f. Now basis f is 1, 2x, 4x squared minus 2, and the coefficients are a plus c divided by 2 and b divided by 2 and c divided by 4. If our goal is only the change from basis E to basis F, then there is no need to compute the transition matrix. Instead, we can only use the definition of coordinates. Consider the polynomial a plus bx plus cx squared, and we want to express this polynomial in terms of basis f. This means we want to compute linear coefficients d, f, g such that the linear combination of basis f equals the given polynomial. After expansion, we have this expression. By comparing the left-hand side with the right-hand side, we know the coefficient of 1 must be equal. So a equals 2g. And the coefficient of x also need to be equal. So we know B equals to F. We also have the coefficient of x squared must be equal. So C equals 4G. From these three equations, we can solve DFG. And the DFG is the coordinate of the given polynomial with respect to basis f. Thus, given any polynomial a plus bx plus cx squared, we can always express it in terms of basis f, where the coordinates are a plus c divided by 2 and b divided by 2 and c divided by 4. In this slide, I will point out one common pitfall when computing the transition matrix. When computing the transition matrix, some students often write 1x and x squared. Such notation is illegal because 1x x squared is not the coordinate of px with respect to f. Because the coordinate vector is always in Rn, which means each entry must be a real number, not a polynomial. So the notation 1x and x squared does not mean the coordinates of P with respect to F, and therefore the meaning of this 3 times 3 matrix is also not clear. It may not be the transition matrix we want to compute. Another common illegal notation is try to write 1x and x squared as a matrix. This is also an illegal notation. When computing the transition matrix, be sure to use the correct notation of coordinates. We have finished section 3.5. I selected some exercises of section 3.5 in page 173 of the textbook for you to practice. You can use this exercise to test yourself. Test whether you really understand the materials covered in this section. The answers to these exercises can be found in page 505 to page 506 of the textbook. There are two things to focus on for section 3.5. The first thing is the notation of coordinates. After reading section 3.5, you should know the notation of coordinates, what is its meaning, and how it can be used. The second thing to focus on is the transition matrix. Given two bases, can you use the formula of the transition matrix for computing the transition matrix? This is the second thing you need to focus on. Feel free to leave comments regarding this video. Any suggestions are welcome. If you have any questions about section 3.5, you can post your question here, and if I have time, I will answer your question as soon as possible, or I will ask the teaching assistants to answer the question, or any students who knows the answer can also join the discussion.